Good afternoon. So in the previous lecture, we were discussing about superscalar pipelines and superscalar processors or processors which employ superscalar pipeline. So in this lecture, we are going to see some of the examples of such processors and also a view on how to evaluate the performance of a given superscalar pipeline or how can you compare between the performance of a base pipeline or a scalar pipeline and the superscalar pipeline. So let's start with analyzing the performance of a superscalar pipeline. So as we know, whenever we talk about the performance, we have to talk about what is the total time taken for executing a given program. So we are going to compare what is the total time taken for executing the same program in a scalar processor, and also we are going to compare uh, what is the total time taken if the same program is given to a superscalar processor which is having a degree m. Okay, so this is the idea. So what we do is that first we have to know what is the total time taken or what is the time expected by a scalar processor to complete the execution of a given program. That we already know. It will be using a normal instruction pipeline, as a instruction pipeline which is having a degree 1, which means one instruction issued per cycle. So what is the total time taken? We have already learned the equation. We have already learned how to formulate. So it is uh, k plus n minus 1, where k is the number of stages and n is the total number of instructions. So when you talk about a base scalar pipeline or a base scalar processor, there you will be having an instruction pipeline which can have an instruction issue rate of 1, and the total time taken to execute a program with n instructions is uh, k, the stages of pipeline, plus n minus 1, because the first pipeline, the first instruction in the pipeline will definitely take k cycles. So that is the significance of k there. Then remaining n minus 1 instructions, they will be executed one per cycle. So in total, k plus n minus 1 is the total time taken by a base scalar pipeline. Talking about a superscalar pipeline, talking about a superscalar pipeline which is having a degree m, and that means in a given cycle you are going to issue m instructions. Okay, so you are going to issue m instructions. The instruction issue rate is m. So the first cycle, in the first cycle, you will be executing or you will be issuing m instructions, right? So in the first cycle, you will be issuing m instructions. There are k stages for, take it as the same number of stages. So there are k stages for the pipeline. Okay, so there are k stages. So the first m instructions that were given in the first cycle will have to be executed in the first k cycles. Okay, after the k cycles are being completed, for every new cycle you can have some instructions coming out, and based on that you can formulate the total time taken by a superscalar processor, a superscalar pipeline processor of degree m as k plus n minus m by m, because in each clock cycle you are issuing m instructions. So after the first clock cycle you are left with n minus m instructions, because in the first clock cycle you have issued m instructions. So what remains? N minus m instructions remain, and these n minus m instructions will be uh, issued into the pipeline as m instructions per cycle. So how many cycles are required as n minus m divided by m. So you get the number of cycles required to issue all the n minus m instructions, and putting it, adding it with the k stages or the k cycles required for the first set of instructions, you get it as k plus n minus m divided by m, and that is the execution time for a superscalar pipeline processor. So now we have got the time taken by a superscalar processor of degree m, and also the time taken by a scalar pipeline processor of degree 1. Now what you have to do, you have to compare the performance. So what is the measure that can be used for comparing the performance? It is speed up obtained, right? So now we are going to see what is the speed up obtained. So as you can see, the speed up obtained is the time taken by the base scalar processor divided by the time taken by the superscalar processor. Now doing that, you can get this particular expression, which is n plus a k by 1, n plus k minus 1 divided by n divided by m plus k minus 1, which you can formulate as m into n plus k minus 1 divided by n plus m into k minus 1. So this is the ideal speed up. Ideal speed up, it may not be the same because there are effects of pipeline stalling, but this is the ideal speed up that you can expect the superscalar machine to have over a base scalar machine. So that is it. So that's about the performance of the superscalar processor. If you know the speed up, if you know the time, then you can also compute throughput based on the same equation as we have used in the case of a scalar instruction pipeline. So that's all about the performance. Moving to some examples of superscalar pipeline processors, or the processors which make use of a superscalar pipeline. We'll first start with the one from Motorola, which is Motorola W810 architecture. This can be termed as one of the pioneers of superscalar pipeline processors. Okay, so this was kind of the first machine which was having a superscalar pipeline. So in this case, as you can see in the figure, that is the architecture for the Motorola W810, which is reprinted from the article of Defendorf and Allen. So the features of W810 is that it has combined three different chipsets to be a single chip. Okay, so these three chips include one CPU chip and two cache chips. So they are put together. That is the first change. They are put together to form a single chip. Then it has employed so many advanced techniques for exploiting instruction level parallelism, thus making use of the superscalar pipeline which is being employed. It also supported graphics when it was to support the graphics, it was having instructions also which could support the graphics, and also some digital signal processing applications. Then you can think about this one as a symmetrical superscalar processor, which means it is going to use a symmetrical superscalar instruction dispatch unit. Okay, so there is a symmetrical superscalar instruction dispatch unit which was capable of dispatching instructions, which is two instructions in every clock cycles. For every new clock cycle, this instruction dispatch unit was responsible to dispatch or issue two different instructions, and this was fed into an array of 10 concurrent units, which means that is your pipeline. So you are going to feed this instructions two per cycle to an array which was having a capability to hold 10 concurrent units. This instruction dispatch unit allowed the instructions to be executed out of order, which means it supported out of order completion. At times, it supported out of order issue as well as branch prediction also. Then this branch prediction was just like before, it was done based on the previous experiences or the previous performance of the program. Branches were predicted and instructions were reordered accordingly. Talking about the instruction set, it has almost all the instructions that are available for the previous version, which was 88100. All the instructions which were available in 88100 is available in 88110 also. Along with that, it has got some instructions which could help it to handle the 3D image rendering also. Talking about Motorola W810, it has got separate instruction and data paths, which means instructions flow through a particular set of buses, whereas data flow through another set of buses. Then it had split caches, which means separate caches to hold instructions as well as data. So instruction cache was called I cache, data cache was called D cache. The instruction cache was having 8 kilobytes of storage, which was arranged as a two-way set associative cache. The two-way set associative cache had 2 blocks per set, okay, 2 blocks per set, 128 sets in total, and 32 bytes of information per block. So when you talk about the two-way set associativity, that is all already discussed in the computer organization course. So you can just refresh what do you mean by the set associativity, how you can identify the number of sets. You can work on it and you can identify that it is whatever the values are given here are intact as if in the case of a set associative memory. Talking about the data cache, it was just resembling the instruction set, which means it could handle all the instructions which were available. It could handle all the types of data that the instructions would chose for. So it was capable of handling all such information. Then the cache coherence protocol adopted here was MESI with a write invalidate protocol being used to maintain the cache coherence. So this is all about the Motorola 88110 architecture. The figure is available along with the slide. You can just go through it. You can understand. You can make a copy. Then also understand and prepare notes on whatever was discussed about Motorola 88110. Let's see another example, which is a common example or a recent example of superscalar pipeline processor, that is DEC Alpha 21064 superscalar architecture. So what you see on the right side of the slide is the uh, architecture of DEC Alpha. So this was just like I told before, this is kind of a recent advancements of superscalar architecture. It was developed as a 64-bit superscalar processor. So the primary thing while designing such kind of a processor, such kind of a superscalar pipeline was to enhance the speed of execution, then issue the instruction issue rate, then supporting multiprocessor applications. Also, it should handle the software, which means it should handle the software. The compatibility should be there while you're talking about the software to be migrated from the older machines like VAX or VMS, and similarly MIPS or OSF. Then it had a clock rate of 150 megahertz in the first implementation, which means the first model that was developed for this architecture was having a clock rate of 150 megahertz. Then one important thing or one major difference from difference of DEC Alpha compared to the other versions is that it has got a huge number of registers. So when you say 64-bit superscalar processor, it has got 32 numbers of 64-bit integer registers as well as 32 64-bit floating point registers. So unlike in the other case where the registers are shared between the units, here they have got dedicated units for integers and for floating points. So there are 32 64-bit integer registers and 32 64-bit floating point registers. The pipeline employed here is a 7-stage pipeline for the integer unit and a 10-stage pipeline for floating point unit. The maximum performance obtained for this particular implementation of DEC Alpha 21064 was 300 million instructions per second as the peak, and 150 million floating point instructions per second as the peak, given for a clock rate of 150 megahertz. So this was the peak performance of DEC Alpha 21064. Now, talking about the instructions, all the instructions, whether it be integer instruction, whether it be floating point instruction, all the instructions, whether it be graphics instructions, every one of them were of 32 bits length. Then the first implementation, as I said, the implementation which had a clock rate of 150 megahertz, it had 2 instruction issues per cycle. But in the later advancements, in the later versions or later implementations, it was advanced to have multiple instructions, more than two instructions executing or issued per cycle. Then it uses some hardware support to minimize any pipeline timing hazards, any load delay slots, and any branch delay slots. Then it also uses some interlocking schemes, and it was found that the DEC alpha had faster multiprocessor interlocking and interrupts. One good thing about this DEC alpha architecture compared to the other versions is that it was widely used across various operating systems, and this property of widely being accepted or widely being run across various operating systems was due to the presence of a specialized or privileged software library which had a capability to run a full VMS and OSF version 1 using the various versions available. So the presence of this particular library helped to make use of this particular processor by various operating system. So that completes our discussion on superscalar pipeline and the case studies of superscalar pipeline. So just go through all these architectures and understand the concept and also prepare lecture notes. Thank you.